Hey everyone, welcome back to our beginner question and answer series. In today's video, we're going to dive into two important concepts in PySpark: RDD, Resilient Distributed Dataset, and DataFrame, and discuss their differences. Whether you're just starting out with Spark or looking to brush up on the basics, this video is perfect for you. I'm your host, and I'll guide you through this fascinating topic. Let's get started. First off, let's start with RDD. Simply put, an RDD is a distributed collection of elements that is immutable and fault-tolerant. These elements can be anything, from numbers and strings to more complex data types. Imagine a dataset that spans multiple machines in a cluster. That's the magic of RDD. It allows us to work with massive datasets efficiently and reliably. Let's break down the key features of RDDs so you can see why they're so powerful for big data processing. First up, immutability. Once you create an RDD, you can't modify it. That might sound restrictive, but it's actually a good thing. Why? Because whenever you perform an operation, it returns a new RDD, which ensures that your data remains consistent and safe during processing. Next, fault tolerance. If something goes wrong, say if a partition of the RDD is lost due to a node failure, don't worry. Spark can recompute that partition using the lineage, which is a record of all transformations applied to the data. This makes RDDs very reliable in a distributed environment. Then we have parallelism. One of the biggest advantages of RDDs is that they allow you to perform operations in parallel across multiple nodes in a cluster. This means you can process large datasets much more efficiently. Lastly, partitioning. RDDs are split into smaller pieces called partitions, which are distributed across the cluster. This partitioning is what enables parallel processing, as Spark can work on different partitions simultaneously. Now let's talk about the advantages of using RDDs. The first advantage is flexibility. RDDs can support virtually any type of data, from simple integers to complex objects, and they allow you to perform custom transformations. This gives you great control over how your data is processed. Another key advantage is fault tolerance. As I mentioned earlier, if something fails, Spark will automatically recover your data using the lineage, which is essential in large-scale distributed environments. Finally, performance. RDDs are particularly great for iterative algorithms, like those used in machine learning or graph processing. Since RDDs can cache data, they are highly optimized for tasks that involve multiple operations on the same dataset. So when should you use RDDs? Let's explore a few use cases where RDDs really shine. First, iterative algorithms. RDDs are perfect for tasks like machine learning or graph processing, where you need to perform the same set of operations multiple times on the same data. Algorithms like PageRank and other graph-based algorithms are good examples. Another great use case is real-time data processing. RDDs are highly fault-tolerant and can efficiently process real-time streams of data like sensor data or logs. And lastly, custom data structures. With RDDs, you have complete flexibility to define your own data structures and perform complex, custom transformations. If you need total control over how your data is processed, RDDs are the way to go. So to sum it all up, RDDs are immutable, fault-tolerant, and optimized for parallel processing, making them perfect for tasks like iterative algorithms, real-time data processing, and custom data transformations. If you're working with large-scale data and need maximum control and performance, RDDs are a great choice. Let's understand RDD through an example. Let's start by initializing a Spark context. This is the entry point for Spark functionality. In PySpark, the Spark context connects your application to the Spark cluster. Next, we create an RDD from a simple list of numbers using the parallelize method. This method distributes the data across the Spark cluster. Now our list is transformed into a distributed RDD, and we can apply operations on it in parallel. Next, let's transform our RDD. In Spark, transformations are operations like map, filter, and reduce. Transformations don't execute immediately. They create a new RDD. Here, we're applying the map transformation, which multiplies each element of the RDD by 2. Now to see the results, we need to trigger an action. Actions like collect, count, and save actually execute the computations. In this case, we use the collect action to bring the data back from the distributed environment to the driver node. After collecting the data, we can print the result to see the transformed list. The output is 2, 4, 6, 8, 10, showing that each element of the original list has been multiplied by 2. Finally, it's a good practice to stop the Spark context when you're done processing, freeing up resources. RDDs support 2 types of operations that allow us to manipulate data in a distributed environment: transformations and actions. Transformations are operations that create a new RDD from an existing one. They are lazy, meaning they don't execute immediately. Instead, they are executed when an action is triggered. Let's explore a few examples of transformations in PySpark. The map transformation applies a function to each element in the RDD. For instance, we can multiply each number in the RDD by 2. This will return a new RDD with each element transformed according to the given function. The filter transformation filters elements based on a condition. For example, we can filter out all even numbers from an RDD. This will return a new RDD containing only the odd numbers. Next, we have flat map. It works similarly to map, but each input element can be mapped to 0 or more output elements. This is useful when you want to split or expand your data. For example, here, each number is mapped to itself and its double, creating multiple elements for each input. The union transformation combines 2 RDDs into one. It merges the data from both RDDs, keeping all elements. This is useful when you want to combine datasets from different sources. The group by transformation groups the data based on a specified key. This allows you to organize your data into meaningful groups. For example, we can group the numbers in the RDD by whether they're even or odd. Now let's move on to actions. Unlike transformations, actions trigger computation and return a result to the driver program or save the data to external storage. Actions are what actually execute the transformations we've defined. Let's look at a few examples of actions. The collect action retrieves the entire dataset from the distributed RDD and brings it to the driver program as a list. While this is useful, be careful when using it with large datasets, as it brings all data to the driver. The count action simply returns the number of elements in the RDD. This can be helpful when you need to quickly know how many records are in your dataset. The reduce action aggregates the elements in the RDD using a specified function. For example, we can use reduce to sum the elements of the RDD. This reduces the entire dataset to a single value. Finally, The Save As Text file action saves the RDD to external storage, like HDFS or a local file system. This is useful when you want to persist the results of your computations for future use. To summarize, RDDs support two types of operations: transformations, which are lazy and create new RDDs, and actions, which trigger computation and return results. By understanding and leveraging both, you can efficiently process and manipulate large datasets in Spark. Next, we'll dive into what DataFrames are, their key features, and why they're essential for efficient data processing in Spark. In Spark, DataFrames are distributed, schema-aware, columnar data structures. Think of them like tables in a relational database or DataFrames in pandas, but designed to scale across a distributed computing environment. DataFrames are perfect for working with structured or semi-structured data, such as tables, CSV files, JSON, and Parquet formats. Now, let's explore some key features that make DataFrames an essential tool in PySpark. First, DataFrames are designed for structured data. This means they work seamlessly with data that has a clear schema, like tables or datasets in formats such as CSV, JSON, or Parquet. You can easily read these types of files and load them as DataFrames using simple methods like spark.read.csv or spark.read.json. One of the biggest advantages of DataFrames is their optimized execution. DataFrames use the Catalyst Optimizer and the Tungsten Execution Engine to perform advanced performance optimizations like predicate pushdown, projection pruning, and physical query planning. These optimizations make sure that your queries are executed as efficiently as possible, even with large datasets. DataFrames provide a rich set of API methods for data manipulation that are much simpler and more intuitive than working with RDDs. For example, you can perform operations like select, filter, group by, and ag with just a few lines of code. These operations are similar to SQL queries, making DataFrames a perfect choice for those familiar with relational databases or SQL. One of the best things about DataFrames is their interoperability. You can mix DataFrame operations with SQL queries. For instance, you can register a DataFrame as a temporary SQL table and run SQL queries directly on it. This gives you the flexibility to work with both DataFrames and SQL seamlessly, depending on your needs. DataFrames offer several key advantages. First, they optimize performance by leveraging schema information. This allows Spark to execute queries more efficiently. Second, DataFrames simplify data manipulation. With SQL-like operations, you can easily filter, transform, and aggregate data. Finally, DataFrames support a variety of data sources such as CSV, JSON, and Parquet, making them incredibly versatile for different types of data processing. DataFrames are widely used in several industries and applications. For example, they're perfect for data warehousing and business intelligence tasks, where structured data is processed and analyzed. They are also great for data integration and ETL processes, where data from multiple sources is cleaned and transformed before being loaded into a target system. And of course, DataFrames are essential for data analysis and data science tasks, enabling analysts and scientists to perform complex queries and aggregations on large datasets. To summarize, DataFrames in PySpark offer optimized performance, ease of use with SQL-like operations, and flexibility to integrate with various data sources. Whether you're working with structured or semi-structured data, DataFrames provide a powerful and efficient way to manipulate and analyze large datasets. Moving on, we'll walk you through different ways to create data frames from various data sources, including CSV files, JSON Python dictionaries, and RDDs. First, let's create a data frame from a CSV file. PySpark makes it super easy to load CSV files into data frames. First, you initialize a Spark session and use the read.csv method to load the CSV file. This will automatically infer the schema and treat the first row as the header. Once the data frame is loaded, you can display it using the show method. The df.show output appears on the screen, showing the contents of the CSV file. Next, let's create a data frame from a JSON file. JSON is another common format for structured data, and Spark handles it with ease. Similar to loading a CSV, you can use spark.readJSON to read a JSON file into a data frame. After loading the data, just call show to display the contents. If you have data in a Python dictionary, you can easily create a data frame by using the createDataFrame method. Let's see how it works. Here, we've created a list of dictionaries, where each dictionary represents a row in the data frame. We can use spark.createDataFrameData to convert this list into a data frame. Lastly, let's look at how to convert an RDD into a data frame. If you already have an RDD in PySpark, you can easily convert it into a data frame by mapping the RDD to a row object. Here's an example. We start with an RDD of tuples. Each tuple contains an ID, name, and salary. Next, we map each tuple to a row object, where each field corresponds to a column in the data frame. Let's quickly recap the different ways we can create data frames in PySpark. 1. From a CSV file using spark.read.csv. 2. From a JSON file using spark.read.json. 3. From a Python dictionary using spark.createDataFrame. 4. From an RDD by converting it to a row object and then calling to df. Now, let's take a look at some of the most common operations you can perform on data frames. Feel free to pause the video whenever you'd like to explore each operation in more detail. Let's break down the main differences between RDDs and data frames, so you can choose the right tool for your data processing tasks. First, let's talk about abstraction level. RDDs are the lower level abstraction in Spark. They represent a distributed collection of objects and give you fine-grained control over your data. On the other hand, data frames are a higher-level abstraction built on top of RDDs. They represent structured data in a distributed format and provide a more user-friendly interface for working with that data. While RDDs offer more control and flexibility, data frames simplify many tasks, such as handling structured data and running SQL queries. The data structure is another key difference. RDDs are unstructured. They don't have any inherent schema or column names. This means you can store any type of data, which makes them more flexible but harder to manage. In contrast, data frames have a structured schema. Data is organized in columns with specific types, similar to a table in a relational database. This structured approach makes data frames ideal for handling data that follows a predictable structure, such as CSVs, JSON, or Parquet files. Now let's talk about performance. RDDs offer raw performance, but at the cost of flexibility. Since they don't optimize operations, performance can suffer when performing operations like joins or aggregations, as they lack an execution optimizer. Data frames are more performant. They benefit from Catalyst, Spark's query optimizer, which allows for optimizations like predicate pushdown and physical plan optimization. Additionally, data frames leverage Tungsten, Spark's execution engine, which provides further memory optimizations and better execution efficiency. So, if you're looking for better performance, DataFrames are the clear winner due to their ability to optimize queries automatically. Next up, ease of use. RDDs require you to write more complex, lower-level code for operations such as filtering, transforming, and joining. They give you full control, but require more effort to implement even simple tasks. DataFrames, on the other hand, allow you to express transformations and queries using higher-level, SQL-like syntax. You can use the DataFrame API or even Spark SQL for data manipulation, which makes them much easier to work with. Writing code is simpler and more intuitive with DataFrames. So, for ease of use, DataFrames win hands down. Let's talk about type safety. RDDs are strongly typed, meaning you can enforce the type of the data you're working with, like integer, string, etc., at compile time. This ensures that you catch type-related errors during development, offering type safety. DataFrames, on the other hand, are dynamically typed. The schema is inferred at runtime, so type errors might not show up until the code is executed. This makes them less type-safe compared to RDDs, but they offer more flexibility when dealing with diverse data. How do they compare in terms of SQL interoperability? RDDs don't directly support SQL queries. If you need to run SQL queries, you would first need to convert RDDs to DataFrames and then perform SQL operations. So, SQL compatibility is limited. DataFrames shine in this area. Since they are built on top of Spark SQL, you can directly run SQL queries on DataFrames, making it very easy to integrate SQL-based data operations in your Spark jobs. You can even register DataFrames as temporary views and query them just like a table in a database. Let's move on to operations. RDDs provide low-level operations such as map, filter, reduce, and join. You have complete control over your transformations and actions, but you need to manually manage how these operations are applied. DataFrames offer a rich set of high-level operations such as select, group by, ag, and join. These operations are more intuitive and often much more efficient due to optimization. In addition, they are optimized using Catalyst and Tungsten, so operations like joins or aggregations perform much better. Next, let's talk about serialization. RDDs require serialization using Java or Cryo to store data, and since RDDs often involve object serialization and deserialization, this can lead to performance bottlenecks when processing large datasets. DataFrames use an optimized binary format, tungsten off-heap memory, to represent the data. This reduces serialization overhead and boosts performance. DataFrames also have a much better memory representation, resulting in reduced CPU and memory usage. Let's look at API availability. RDDs have a comprehensive API in Scala, Java, Python, and R, supporting low-level data manipulations. However, since it's lower level, it's more verbose and harder to work with. DataFrames also support APIs in Scala, Java, Python, and R, but their API is more user-friendly and high-level. You can perform data manipulations and queries with fewer lines of code and in a more readable way. The API also provides better integration with Spark SQL, making it more accessible for those familiar with SQL. Finally, let's talk about support for advanced analytics. RDDs offer flexibility, allowing you to implement custom transformations and complex analytics. However, for advanced analytics tasks such as machine learning, it requires you to implement everything manually. You would need to perform feature extraction, transformation, and model training using raw data, which can be cumbersome. DataFrames are better suited for advanced analytics tasks. They integrate well with MLlib for machine learning, GraphX for graph analytics, and other advanced Spark libraries. You can use high-level APIs to build machine learning pipelines, run statistical analyses, and more, making it easier to work with advanced analytics compared to RDDs. To summarize, RDDs give you fine-grained control and are best suited for custom, low-level operations and complex data processing, while DataFrames offer better performance, ease of use, SQL compatibility, and more powerful abstractions for data analysis. If you need raw performance and type safety with manual control, RDDs are the way to go. If you're looking for optimized performance, easier code, and strong support for SQL and advanced analytics, DataFrames are your best bet. So, when should you use RDDs and when should you use DataFrames? Here's a quick guide. Use RDDs for low-level transformations, unstructured data, fine-grained control over computation. If you need low-level control over your data, or if you're working with unstructured data that doesn't have a schema, RDDs are a good choice. Use DataFrames for structured data, SQL queries, optimized performance. Now that we've explored the differences between RDDs and DataFrames in Apache Spark, the decision ultimately comes down to your use case. RDDs provide low-level flexibility and are ideal for complex, unstructured data, while DataFrames deliver higher-level abstractions, schema enforcement, and superior performance for structured data. Understanding these topics can help you make the right choice, whether you're optimizing performance, scaling your big data solutions, or crafting custom processing workflows. Thanks for joining us on this journey through PySpark's powerful data processing capabilities. If you found this video helpful, don't forget to like, share, and subscribe for more insights into big data and analytics. And as always, keep innovating and keep building. See you in the next video.